Okay, welcome back students, and today let's start with the fourth chapter in the Transducers Engineering Unit 1. We have already almost covered the static characteristics of a system or a sensor, and then the different kinds of sensors, and then in the last chapter we have covered extensively about the different kinds of errors and the static parameters that we have seen. And today in our unit, we will be able to cover the dynamic characteristics of a system, okay, or a sensor. Whichever a sensor here contributes only to the system, and the system can be overlapped with the sensor in our case of transducers. As we have seen, there are two types of characteristics for any sensor. One is the static and then the dynamic. For the static, we have seen several parameters there like linearity, precision, accuracy, lag, and all these things. And the dynamic characteristics, now what we are going to see, are all interrelated with time, and the static characteristics are all not related with time, and they are just the very typical non-variant characteristics that you are able to observe from a sensor. And if you take a sensor, it is totally not dependent on time, but the dynamic characteristics of a system are dependent on time. That is the main difference between static characteristic and a dynamic characteristics of a sensor. Take an example. If you are able to measure 100-degree boiling point of a water, okay, 100 degrees the boiling point of water, and you are using a physical thermometer from your laboratory, that physical thermometer, which you can consider it's a calibrated thermometer, is an ideal thermometer, and it is calibrated, and it should give only 100 at any number of times, and there occurs the problem of accuracy and precision, and it is not going to vary at any cost anywhere. Okay, it is not time variant. But there are several other parameters. Okay, imagine now you are going to measure some vibration in a system, okay, of a motor. Okay, you have fixed an accelerometer sensor over the motor, and you are starting the motor as an impulse. Okay, you are starting and stopping. Okay, that is an impulse action. Okay, there you are able to measure the acceleration what is generated inside the motor using the accelerometer. There occurs what is the variation that has occurred with respect to time. Okay, here comes all the dynamic parameters of a system. Okay, so here you find the dynamic nature of a system. Now, as I told you, you are going to have an important discussion on dynamic characteristics. For example, we are taking a sensor. The sensor is thermometer, and we are going to drop this inside boiling point of 100 degrees centigrade water. So here two types of actions will take place when you drop a thermometer inside 100 degree of water. Immediately there will be an overshoot of temperature inside the thermometer, so that suddenly it will rise. Okay, that is called as transient response. Suddenly a rise will occur there inside the system or your sensor. That's called as a transient response, and it will come to a steady state. What is your steady state now? It is the 100 degrees centigrade, a steady state. After some amount of time, okay, that is the steady state response. So any sensor with the dynamic characteristics, when we are going to study, then there will be a transient response and a steady state response. That's what we saw now. There is going to be an addition of the transient response with the steady state response, and finally we will be able to reach this 100 degree centigrade. This is indicated as, this is the C of t is the function, the final output, and C of t, okay, that is your transient response, and then Cs of t is your steady state response. This equation gives you the entire dynamic response of your system. Okay, so we have made it clear that for any kind of a system we are going to take the dynamic response, and for dynamic response there are two factors involved inside, and that is, one is your transient response and the other one is the steady state response. And the transient response is the contribution that it is related, that it is giving an immediate overshoot and it goes to zero. Okay, and the steady state response is the one which it goes till infinity, that is, it should maintain till infinity the 100 degree centigrade of water. That is not, it's not going to change. Okay, that's what the steady state response and the transient response, that is t is equal to, here in the steady state response it goes till infinity, and here it is t is going to 0. Next comes, what are the different kinds of parameters involved in the dynamic characteristics of a system. What are the parameters involved? The first one is speed of response. The second one is measuring lag. The third one is fidelity, and the fourth one is dynamic error. Okay, we will see one by one what is speed of response. When you drop in a thermometer inside the water, how fast it responds to, and this action of dropping inside 100 degree of water is called as the speed of response. Okay, how fast it reacts to the input given, how fast the system acts to the input. Second one is measurement lag. Here we have two actions. One is the retardation lag, the other one is time delay lag. Here this lag is again very similar to the response, but some systems immediately responds or acts to a input and some acts with a delay. Okay, that acts without any kind of a delay is called as a retardation lag, and which acts with a delay, it's called as a time delay lag. Next comes our fidelity. Fidelity is a factor which decides the entire erroneous result, whether it is there or not, and how reproducible and how much it is non-erroneous is decided by the fidelity. How much this dynamic error is not present, is error is not present over time. Dynamic error is very simple, very similar, how much error is present or not, that is the actual minus the measurement error that we have seen already with respect to time. Okay, that is the main factor, the actual minus actual measurement minus the measuring standard. All those things gives you the error, and then when this error, how much it is present over time, gives you the fidelity. So for these are the four important factors, the dynamic parameters that you are going to see, and we have seen in this dynamic systems. Next comes how we are going to analyze this dynamic characteristics. Analysis. Time domain analysis is the one which is only dependent on time, and frequency domain analysis is the one which is dependent on the frequency also. It's also involved with time and also it is frequency. And before we go inside how we are able to analyze the time domain and frequency domain analysis, here we will need to know what are the different kinds of inputs that we can give to a system to analyze the time domain and frequency domain. Because when you know only what are the different kinds of inputs that can be given to a system, then you will be able to understand the time domain and the frequency domain of a system. What are the inputs that can be given to the system? The first one is the most important for the time domain analysis is the impulse response, impulse signal. The next one is step signal. The third one is ramp signal. These three are the main different kinds of signals that can be given to the system for analyzing of the time domain analysis. And for the frequency domain analysis, mainly you are going to give the sinusoidal signal. Now we will be seeing why we are giving the impulse system, the step signal and the ramp signal, how they look like. This is your step signal respect to time, the impulse, then this is your step. Okay, so see here, so in your time domain analysis, to make your time domain analysis happen inside a system, you need three different kinds of inputs. And here you have your impulse signal, you have the step signal and then the ramp signal. A step signal is a one which is you are going to give a constant input inside a system. Example is very typically this 100 degrees centigrade of water where we are going to drop our thermometer inside. This is a step signal. Okay, but imagine it's a, you want to make it as an impulse signal. Okay, you are going to just dip and then take out. That is an impulse signal of a thermometer. Okay, and a ramp signal is the one, it is going to constantly increase. Okay, imagine you are going to increase it from 0 degree to 100 degree. That is, you are going to put in a thermometer from inside a ice and then you are going to increase the temperature putting in a heater. Okay, there you are going to increase from 0 to 100. There it is from 0 to 100 degree centigrade. Here it will be a ramp and there it will be linear in nature. And here it is directly you are going to drop in the thermometer inside a heater which is boiling, and here it is an impulse where you are going to just dip and then take out. Okay, here it is an impulse signal and here it is an sinusoidal signal. As you all know, a sinusoidal signal can be represented as sin omega t, where omega is 2 pi f, where f is the frequency. Okay, so sin omega t is represented here as it is time and versus the magnitude. Okay, so there are two factors involved here. One is, continue, let's draw again a sinusoidal signal. There are two factors involved in this. One is your magnitude. Okay, both are constant. The magnitude is also a constant signal and then the phase is also a constant signal. So for this reason of introducing frequency, we are going to have this sinusoidal signal, sine signal, for the frequency domain analysis. Okay, we also have, instead of the along with the impulse signal, unit signal and then the ramp signal, a parabolic signal also. A parabolic signal looks like this. Okay, so this is a parabolic signal. Now we will look into what are the different kinds of systems that are available with us. There are several different kinds of systems in the world that can be realized. First we will have an overview of what are different kinds of systems that we can have. A thermal system, a mechanical system, an electronic system, an RLC, that is resistance, inductance, capacitance network, all these things combined, a physiological system or a biological system. Okay, all these things can be converted into models. And why we need to convert into model? We need to know the simulation and then only we need to work out. Okay, we can't give introduce an input without knowing how it is that is going to work. Okay, we need to first know how a system is going to work, and then only we can work with the system. For that, imagine you are going to work with the human body by giving in a drug. Okay, can you give directly a new drug to the system? No, it's not. So you need to create a model of a human body, okay, mathematically, and then you can give different kinds of drug systems there as mathematical models, and then you have to work. Like the same way, a boiler can be converted into a boiler means a boiler is a one which creates steam, which can be converted into a thermal system using the mathematical model of using thermal modeling, and then you can give different kinds of inputs with assumptions, and then you can convert. All this kind of things will be all the things which I taught here on modeling of different systems will be taught to you in detail in the paper of control systems. So we will have only a glimpse of all these things. So models of a system. There are three types of models that we are going to: zero order, first order, second order. For all these things, we will take the main unit step. Okay, how a unit step looks like something like this. Okay, this is the zero order, first order, second order. Okay, I will first give you some examples of a zero order system, first order system, and second order system, so that you can all imagine about how the zero order system work, or a first order system work, or a second order system work. Then when we give you an input, then how they will respond. Okay, first we will look into a zero order system. Simply a switch, an on off switch, okay, is an zero order system. You are going to give an input, immediately it's going to respond without any time delay. A zero order system responds without any time delay. Okay, you are going to switch on the switch, and then it's going to give you the light. Okay, this is a zero order system. And also, if you want to take another one, everybody might have known about a linear potentiometer. There is a rheostat, which you might have studied in your secondary schools to change the current values. That is a zero order system. You are going to change the slider, and immediately you will see the action that is happening there without any time delay. Okay, so this is a zero order system. The first order system, our home fan, is a first order system. You are switching on. Okay, you don't get the, let's take, you are going to switch on the fan at the maximum speed of 5. Okay, or the maximum speed, and let the fan rotate at an rotations per minute or 400 rotations per minute. Okay, in that 5 or at the maximum speed. Whether it will rotate immediately when you switch on the switch? No, it won't rotate immediately when you switch on the switch. It will take some time, and then only it will go to that maximum speed. So there is a time delay where there it is related, and then only it will reach the whole maximum. Here the time delay occurs. Okay, so wherever there is a system with there is a time delay, then that's kind of a system is a first order system. So only a time delay is there with the respect to the system, then that's a first order system. Then we come to a second order system. A second order system, apart from having a time delay, it will have some oscillations in between. Okay, then these are some complicated processes like a reactor or a stirrer and all these things. There will be, it will take some time, and it will oscillate up and down, and then slowly it comes to the steady state, or this, what is the set point, what it is given. All these things will be in detail you will study in control systems. There are 5 units there in that semester itself. Now we will have a look into how a zero order system will react when there is a unit step is given. You see here, unit step. Okay, this is the amplitude. When you give the unit step input, immediately there will be a response. It will be a typical linear, but for a first order system, when you give an unit step response, it will be something like this. This is the delay that has occurred. So are you able to understand? We are giving in a linear system. Here you are immediately, for each one is a point, and when you give, this is the first rotation, second rotation, third rotation, immediately it goes and increases to this next levels. But here for the first level itself, it takes some delayed time and then only it increases. But for a unit step function in a second order system, it is something like this. See here. So here in a second order system, you are having, let us take, this is your fifth rotation or the highest speed what you want to give. It takes some time. This is the time taken, and apart from that, it is oscillating in the top and also in the negative regions, and slowly it comes and settles down. So these are the different kinds of systems, and then first zero order, first order and second order, and how they react to a unit step. All these things have reacted to your unit step input. Okay, so you are understanding, we are giving in a unit step signal, and then we are seeing the response out from a zero order, first order and a second order system. Okay, in the second order system is the most important thing in our study, and here there are some parameters involved. We will see these parameters. Here there is no, it's immediately increasing. Okay, can you see everywhere there is an immediate increase. This won't increase in this fashion. Okay, there it will be an delay very similar to this. There will be a delay and then only it will increase. I will draw here separately. You are giving in the input here, but it is increasing. It starts only here and it comes down. Okay, so these are the main things. You are giving in a unit step response and then it takes some delay. This is the delay taken. This is the delay, and this is called as peak time. Peak time, and we also have, this is the overall time to reach your set point. This is your set point, or this is the set point, or your maximum time that is have reached for something like a fan to the maximum speed is your set point, and this is that set point, and it has the overall time. But the overall time is also not set up and it has not reached exactly to that time. Okay, let's take this as 400 rpm. It is not at reached to 400 rpm, it has reached only to 380. Okay, so this is this delta, this is the error. Okay, so this is the settling time or the overall settling time. Okay, this is a peak time. Okay, so we have studied about the set point, delay, and then the peak time, overall settling time, and then the error, and finally the whole set of parameters that are involved with secondary or the second order system. All these things are very important, and you will study all these things in the subject named control systems. So To summarize, we have today seen beautiful things on our systems, that is the dynamic characteristics of a system, and we have seen the different kinds of parameters involved there, and then how to analyze each thing, okay, and then the frequency domain analysis, time domain analysis, and then the different models of a system, that is zero order, first order, and the second order, and how to, for analysis of a second order system, what are the parameters that we need here. All these things have been told. And finally, to sum up, I will say the final one thing which is left out, that is the in frequency domain you will also have the frequency attached with this. In this thing you are seeing only the amplitude, and here if you want to separate out the frequency, you will apply the Fourier transform, and finally you will get along the frequencies what are all involved in this system. Okay, this is the frequency domain analysis. Okay, so to summarize things, we are also applying the frequency domain analysis so that we can also extract the frequency involved in this parameters. So thank you students, we will again meet you in the second unit.